So I guess we are almost ready to start. I hope the voice is coming from me. Maybe wait a few seconds.
We hear you great, Lorenzo. Thank you.
Thanks a lot. Maybe we wait a few seconds more to allow other people to join, and obviously we welcome all the ones that are already connected. I profit of this few seconds to say, okay, what you see on screen is that the fact that the webcams and the microphones are switched off, but there will be a session of questions and answers at the end of the discussion. In any case, you can submit, and we are invited to submit your comments, questions in the chat. The session is recorded for being then available later on the website. So in case you know that it's recorded, personal data are not shown in the recording. And I guess we could go to the first slide if Virginie and François want to go to that one. So we show also the link to the project. Great, here we are. So you see the abc21.eu link at the bottom of this slide. The project, as you might know, is a collaboration between Africa and Europe on reviving, updating to the conditions of this century, the changing climate, the changing level of urbanization. So the aim is to document examples of bioclimatic architecture and discuss how this tradition from the past can be projected into the future. But it's a collaboration between a number of partners in Africa and in Europe, and you will find the entire list of partners and allies that are supporting us on the website. Another thing that I need to say at the beginning is that the final conference presenting the project and all the results of the project will be in Morocco, in Ifrane, on 3 to 5 May, so a little more than 1 month from now. There is still time to send abstracts for papers to be presented to the conference till the 14th of April, a very last minute possibility. And I think I would give the floor to Virginie and François for this webinar on case studies.
Thanks, Lorenzo. We are activating our microphone. Can you hear us? Yes, is that fine?
Fine.
Okay, great. So we start the webinar. So thank you. Welcome to everyone. So we start the webinar, and I introduce the aim of this webinar. So to come back about the goal of this European project, the main goal is to increase the energy performance, quality of life, and sustainability of West African buildings. There are 4 interconnected objectives. The most important one, the one which is related to this webinar, is the first one, and I just read, this objective is to identify, report, and strengthen bioclimatic designs and local materials in Africa and Europe. And to reach this objective, we have identified 24 case studies in Europe and Africa, including La Réunion, which is a remote French island in the Indian Ocean on the west coast of the big island of Madagascar that you all know. So all these case studies have been selected. So first of all, we wanted to prove to public and private sector and also to policymakers that bioclimatic buildings can be comfortable and affordable. Most of the time, people are in the mind that bioclimatic buildings cost more money than a standard building, and we try with this project to prove that this is not the case. The case studies have been identified thanks to their passive strategies, and they must have energy efficient systems as well. Affordability and replicability are two important criteria, and we have to have solid data and users' feedback to be convincing. So we have to prove that those buildings are bioclimatic, they are comfortable, and the users are happy to live and work in this kind of buildings. That means that we need measure data, we need to have surveys to have this feedback. In terms of location, we have selected 5 case studies in Europe, 13 in Africa, and 6 in the island of La Réunion. What we realized is that when we looked for case studies in Africa, there is a lack of data in Africa. So in terms of improvement and gain in this project, thanks to this project, we will be able to have feedback, measure data in most of the African case studies that we have selected. That means that we have launched measurements campaign that are started a few months ago. So in terms of thermal comfort.
Yes. So just a few words, because the main purpose of this webinar is to analyze these buildings in terms of bioclimatic design, but also thermal comfort conditions. So the thermal comfort is defined as that condition of mind which expresses satisfaction with the thermal environment. So the comfort is generally based on different environmental factors, such as the air temperature, the radiant temperature, the relative humidity, and the air velocity that we can measure thanks to spot measurements or continuous monitoring. But also the thermal comfort is based on personal factors that can be physiological, psychological, or other aspects. The most important one that you know is the clothing insulation, the metabolic rate, but there is also phenomenon that has been studied, like the adaptation, the acceptability, and so on. So these aspects are generally studied thanks to questionnaire surveys.
So to reach thermal comfort in hot climates, the air velocity is very important. In terms of natural ventilation, in all the buildings in European and in all over the world, we can identify 3 different kind of ventilation. The first one is the one that we use in air-conditioned buildings, is used for just hygienic purposes. And so the level of air change rate per hour is just 1 air change rate per hour. The second type of natural ventilation is used to evacuate the internal loads. In that case, we need to have 10 air change rate per hour. And the one which is more important if we want to create an air velocity on the users is the one which is delimited by this rectangle. The aim is to create an indoor air velocity of 1 meter per second on the users. In that case, we need to have very high level of air change rate per hour. 60 is the minimum. In terms of thermal comfort, the comfort zone is the blue zone and is defined and can be influenced by the air velocity, which is on the x-axis on the diagram, and the air temperature. So as you can see, the more the air velocity on the equipment is important, the more you can feel comfortable to high temperature. For instance, an air velocity of 1 meter per second with an air velocity of 1 meter per second, the user, if the clothing is appropriate, can feel comfortable up to temperature like 30 degrees. And if we don't, and this air velocity is generated by a difference of pressure between the two facades of the building. That means that we need to have narrow buildings so that we can use this natural cross ventilation. In case we have no wind, ceiling fans have a crucial role because they can create the air velocity that, in case we have no wind, but that we need to have a feeling temperature which can be reduced by 4 degrees. For instance, if a user has an air velocity of 1 meter per second and the temperature is 30 degrees, the temperature that the user feel is 30 degrees minus 4 degrees, which is 26 degrees. So he can feel very comfortable. So ceiling fans can be a very important, and it can be replaced. Air conditioning can be replaced by ceiling fans.
So to measure and to study the thermal comfort in the different buildings, we define 3 different levels of monitoring. So the first one is a basic level of monitoring where we only put temperature and relative humidity sensors inside the room. The level 2 is the intermediate level. So we add outside a weather station. So inside the room, we still have the smart sensors, so the temperature and relative humidity sensors, and outside the building, so we decide to install a weather station. And the next level, so the detailed level, so like the first 2 levels, we have the air temperature inside, the weather station outside for the different physical variables, but we also have the measurement of air velocity and globe temperature inside the building. So the inside is more detailed. And here we have the different levels for all the 24 case studies that we have selected. So just to show you that we only have 4 buildings with the basic level, and most of the buildings we try to have the detailed level, and especially for the African buildings, where most of them are in level 3. So we have detailed monitoring. So now we are going to focus this webinar on 4 case studies that we have selected. So Alessio and Lorenzo are going to present you the 2 case studies in Europe. So the Réunion house in Portugal and also Botticelli in Italy. Then I will follow the presentation with the Mbakadou School in Senegal. And finally, François will present the Ezura building in La Réunion. So now I leave the floor to Lorenzo and Alessio.
Yes, thanks. So here is a presentation from Lorenzo Silvia Erba, who is also coordinating with me the entire project, and Alessio Battistella. The first case study is this single family house located in Sicily. I think we can go straight to next. So the building has passive features, and one which is quite important is the external insulation of the envelope. So this house is certified passive house and Casa Clima. it has 20 centimeters external insulation, high performance windows, and a few other passive features, natural ventilation, especially at night during summer, obviously, and an exchanger of air, ventilation air is pre-cooled through the ground. I think we can go straight to next. Then obviously the protection from the solar radiation is given for the opaque walls by the external insulation and the thermal mass of the structure. There is protection from direct radiation, so automatic controls on the external blinds, and there is this ground exchanger. Next. We have a very detailed monitoring system here for air temperature, globe temperature, humidity, air velocity, indoor air quality, also measurements of visual comfort, at least the luminance. We go on to the next. And in this building, we have also, since we have 3-4 years of monitoring, we have also the complete monitoring of the energy uses, which we don't show here for each equipment in the house, and the energy generated by the photovoltaic on the roof. Since the energy use is so low, thanks to the passive features, the building in fact generates more energy over a year than it uses over a year. But if we go to month by month, there is still an unbalance between what is generated on the roof in December and what is used in December. So it's a net zero energy building. If we do a balance on a year, which is a not very realistic balance, if we do it month by month, it is close to zero because of this high reduction of energy use thanks to passive features. Next. From the thermal point of view, apart the green room, which is a room not often used and not controlled, the others where the controls are active, the yellow and black rooms, the living room and the bedrooms, remain for the entire year within the comfort zones, which are fungier during winter when there is active cooling, active heating, and the adaptive changing comfort band in the other seasons. Next. And so we can see, for example, for a small couple of weeks, that the external temperature is going to 38, and indoor we have this green line which describes the operative temperature in one room in free floating with no active cooling, remaining in the adaptive comfort range. Next. And now to architect Alessio Battistella.
Okay, good morning to everybody. So in this case, we decide to present a case study which is located in a historical center. So the building are there is a kind of dense system. So the idea is understanding how we can have a comparison between this kind of materials and the way how we can maintain techniques that come from the tradition. So we are quite near to 40-minute driving from Lisbon, and quite near to Évora. As you can see, this house is made with rammed earth. So the technique is the pisé, and they push forward this technique and maintain it as a facade. So you can see it. There are no plastering, just to demonstrate that we can do it, just with a little of architectural solution, as for instance putting this layer, you can see on the right of the slide, layer by layer of stone that avoid the washout of the wall. And in the internal walls were made by straw and earth. The straw is a waste product from the agriculture, so it is quite strong the idea of circularity in this building. The photovoltaic system, when you can also in the winter time give energy to a heating system, and when there is no sun, they use a kind of oven, a chimney with high performance, and there are no air conditioning, and so with just the thermal inertia, this very interesting solution, they get to maintain a quite comfortable situation. Also, the ventilation is quite interesting. They create a patio in the entrance, which is in the right part of the slide, and in the left, in the right, they have a garden, and so in this way they can have also a quite efficient cross ventilation. So again, just with passive principle in a warm weather, they get a quite interesting, comfortable situation. Next, please. So here you can, we are in the level 1, the first level of the survey in terms of data. So here you can find where we put the sensor. So we have also an outside sensor that help us to define the difference between indoor and outdoor. Next. And here you can see that there is a quite interesting gap between external and internal, and night and day. And so just with a night ventilation, we can get quite interesting value also in terms of again in terms of natural ventilation. Next, please. I leave the floor to Virginie.
Yes, thank you, Alessio. So now I'm going to present you the Mbakadu School in Senegal that was designed by the ASF Italia. So the building is located in the region of Louga in Senegal, which is, we can see on the picture that there is only some shrubs and there is not a lot of buildings. And the Mbakadu School is composed of 3 buildings. So the first one was done before the project, and it was in cement. And the 2 other buildings I'm going to present you the bioclimatic principles. So here we have the different bioclimatic strategies that have been implemented in this building. So the asset of the building and the strong points that we can retain is that they try to work on the high thermal mass of the walls and the roof, to think about solar shading with the large roof overhangs, and also to use local materials. So how you can see that the foundation of the building were made with sandbags. The walls are made of mud bricks that are really thick, with 40 centimeters. And the roof, so it's a traditional thatched roof in Tifa that is also very thick with 35 centimeters. All the structure of the roof is made of wood and bamboo, local bamboo. And also the particularity of this building is that we have simple small openings with no glass. And of course, also the floor of the building is made of earth. So for these buildings, we are in the level 2 of the monitoring strategy. So here we can see the position of the temperature and relative humidity sensors in the different buildings. So the sensor meter 1 and meter 2 are placed in the buildings that was described before, so in wood bricks and Tifa. And the third one was in the building in cement. And also we can see the position of the local station that we have, that the team on site installed for the project, which come from the project TAMO. So here we have an analysis of the data that are exported from the temperature and relative humidity sensors in terms of Givoni comfort zone. So here we focused only in meter 1 because the 2 classrooms had approximately the same results. And what we can see here in the Givoni diagram, if we compare the results for the temperature and relative humidity inside and for the outside, is that there is less dispersion of the points inside the building. And here we can see the impact of the high inertia of the materials. And also what we can see is that most of time the points are outside the zones, but it's because of the low level also of humidity. And here we can see that for these conditions, if we can have and achieve an air velocity inside of 1 meter per second, we will have only 45% of the points that are in the comfort zones. So then we try to analyze the data in terms of air temperature profiles for a representative week in summer, where the global radiation all the days were superior to 800 watt per square meter. And the most important things that we highlighted here is that we can have a difference of almost 5 degrees between the interior and the exterior during the day, so when there is the maximum outside. And also we can see that the diurnal air temperature variation is really different inside and outside. So inside we only have a difference of 8 degrees between night and day, between the lowest and the highest points, while in the outside we can reach 18 degrees Celsius of difference between the lower air temperature and the highest air temperature. Also, what we saw there is that there is no thermal lag, and we can also confirm the impact of the high inertia of the materials. Finally, also what we can see is that the temperature is the highest during 12 o'clock, from 12 o'clock to 7 p.m. in the evening, and that the temperature is the lowest from the beginning of the day, so from 2 a.m. to 9 a.m. Also, we try to see and analyze the data in terms of wind profile and also in terms of wind potential for these buildings. And what we can see is that the wind speed, the mean wind speed during the occupation hours, so from 8 to 6 o'clock, is almost 2.3 meters per second. And that we can use natural ventilation from 8 to 11 a.m. because the temperature is lower than 30 degrees. But then when we saw that there is the high potential in terms of winds, but it's also the time where the temperature are very high and are more than 30 degrees. So normally where we cannot use natural ventilation because we will have hot air in the building. So what we learned from these first results is that we can, and what we can recommend is that we can use the wind, the wind from the outside, and so to improve the air velocity inside when the air temperature outside is below 30 degrees. But then when the temperature outside is more than 30 degrees, the idea is to minimize the use of the openings only for the hygienic purpose. But then to use the ceiling fans and maybe the evaporative cooling to help decrease the air temperature of the room. And the different solutions that can be considered is to collect water from the air during the night, because during the night the air temperature is very low, and that it could be possible to have condensation on a corrugated iron sheet. Or we can use systems like fog collectors when there is fog, or as they done it before on another case studies that we did not present here, but in Senegal, they dig a well to collect the water and then reuse it in an evaporative cooling system. And the way to also then the step 2, the idea is to use water mist spray system during the day to help decrease the air temperature. Thank you. So I leave the floor to François.
Thank you, Virginie. Now I'm going to, so we move to La Réunion. So we leave Senegal and we move to La Réunion. And so as I said, La Réunion is a small French island located in Indian Ocean. You have an aerial view of the building Ézirois, the Faculty of Engineering Ézirois. We can move to the next slide. Yeah. So this is the first time that we use the wind to design a building. So the architecture of this building has been clearly influenced by the wind. So what we did during the first stage at the design stage, we gave to the design team all the data that were collected thanks to local weather station that we have on site. So the design team had lots of data, 10 years of data on the past 10 years. And we asked them to analyze those climatic data. During the opening hours of the building, what was important is where was the main direction of the wind during the daytime and during the hottest months. And it appeared that the main direction of the wind, the trade winds, were mainly east and southeast. That's why the architect had the idea of, in terms of shape, to have to create a C shape. The plan view of the building, you can see that the architecture has the form of a C, and the C faces the trade winds. So why this? Because as I said, we have to create natural ventilation, and to create natural ventilation, you have to have a difference of pressure between the two facades of the building. So when the C faces the wind, inside the sea we have a high pressure zone, and on the other facade, because of the law of Bernoulli, the wind accelerates, and we have a low pressure zone. And thanks to the difference of pressure, we can create air velocity into all the spaces of the building. To validate this, we asked to the design team to create a model of the building, and the model of the building at the design stage were tested in Paris at the Eiffel laboratory, just to confirm that the architectural solution perform well. And it appears that the natural ventilation worked well thanks to the wind tunnel tests that were made in Paris. So in terms of bioclimatic strategies, except the one about the natural cross ventilation that I've already explained. So the main features are all the spaces are naturally cross ventilated. We use low inertia materials. We use a material that is called dampalon. Dampalon is polycarbonate that is very thin, only 16 millimeters, and it allows the natural light to enter in the building. We use solar shading systems, and we ask to the design team to put the solar shading system detached from the openings so that we can use natural daylight. Vegetation was mandatory around the building. Vegetation and trees can reduce the air temperature by 4 degrees compared to a building that have just mineral pavements. And then in terms of energy efficient system, ceiling fans were installed in all rooms. So then in case we could not use natural cross ventilation, we use a low pressure shaft because we had some spaces where the pressure was exactly the same on both sides. So the low pressure shaft, few buildings have been designed in all over the world. The idea is to create a shaft, and thanks to Bernoulli effect, to create a high pressure. It's like a chimney, and thanks to this chimney, we have a low pressure. And the air velocity is, so the wind comes from the high pressure facade. And as you can see on the picture, the blue arrow show the path of the air velocity inside the building. And as you have pictures of the low pressure shaft underneath the chimney. We could plant some plants. So in terms of visual effect, it's a very pleasant atmosphere for the users. Here we have a typical office. So instead of having just one people for one office, the size of offices are 66 meters deep and 3 meters wide. And for each office, we have 2 people. In terms of passive design, the desk, so we work with the architect into the indoor design. So the desks are parallel to the airflow. We use vertical louvers so that the users can adjust the air velocity. The dampalon is used for using natural light. Even the seats had a design, specific design. The back of the seats have a mesh, so that when the user is seated, he can exchange with the air and without sweating. And one very specific detail, which is very important, when you have lots of air movements inside the offices, you have the risk of the door to close due to the air movements. So we ask to the architect to install a magnetic door stopper to avoid the door to close due to the air movements. In terms of energy efficient solutions, in terms of artificial lights, we have LEDs in all the spaces. We have energy efficient ceiling fans, 1 fan per user. So the rule of thumb that we use is 1 ceiling fan for every 10 square meters. And we don't have any air conditioning systems in those offices. So I leave the floor to Virginie to explain the monitoring results with this building.
Okay. So for this building, we are in the level 3, so the detail monitoring, and we have a weather station on site that is very close to the studied building. And also here you can see the ground floor and the first floor plan of the buildings, where we installed some sensors. On the ground floor, so 2 classrooms were monitored in terms of air temperature and relative humidity, thanks to smart sensors. But also we did spot measurements with the testo comfort station in the different classrooms that are in the ground floor. And also in the first floor, we have 2 offices that have been monitored on the different facades, and also another classroom in the first floor. So here you have the results in terms of Givoni comfort zone for 1 year, so from March 2002 to March 2003, in different type of rooms, and also for the outdoor condition. And what we can see here with this diagram is that the number of hours in the 1 meter per second comfort zone is superior to 95% in all the rooms. And so it could be possible to achieve comfort conditions inside the rooms if we have 1 meter per second. So then we try to select 1 week and see the results in terms of profiles. So first, we have here the representation of the solar radiation and the wind profile for the selected week. And here you can see that the 4 first days are almost representative of the days that we have in Saint-Pierre during the summer. So we have sunny day during the morning and cloudy conditions with mostly cloudy conditions during the afternoon. And then we have also 3 sunny days at the end. We have different categories of wind. So during mostly of the first days, the wind speed was lower, with the mean wind speed around 1.7 meters per second. While during the 3 last days, where we have sunny conditions, we also have higher wind speed with a mean wind speed around 5 meters per second. And so here we have the air temperature profiles for some selected rooms of the buildings, and also the air temperature outside the building. So what we can see here is that during the first days, where we have lower wind speed, the air temperature bill is could be equal in some conditions, but it generally below the outside condition. Also, when we have higher wind speed, this difference for the maximum of temperature inside and outside is more pronounced. So we can have a difference of 1.5 even to 2 degrees of difference from the inside compared to the outside. And also we can see that the temperature variation inside the building is lower than outside, because inside the building we only have we can have a difference of 2 degrees between the lowest air temperature compared to the highest, and while outside the air temperature variation is higher with 6 degrees. And here you can see that most of the rooms they are in the ground floor, the first floor.
So then we move to the post-occupancy evaluation, the results from the questionnaire. With two different days. The first day was the 13th of February. In February, in La Réunion, as we are in the southern hemisphere, February is one of the hottest months of the year. So we interviewed people at the beginning of the classroom and in the end of the class. They were asked in terms of thermal sensation. That means that they have to reply whether they felt very cold to very hot. And they were asked about their thermal judgment, which is more, how do you feel? Do you feel this environment comfortable? And the scale varies from comfortable to very uncomfortable. So in terms of thermal sensation, at the beginning of the class, for instance, you can see that 11 students felt neutral, neither cold and neither hot. So most of the class, so for us, the most important is that the majority of the people answer neutral or slightly hot. If this is the case, that means that, let's say, the comfort is achieved. And in terms of thermal judgment, the goal is to have a scale between comfortable and slightly uncomfortable. And in terms of thermal judgment, you see that during this day, most of the students in the class felt this environment comfortable or slightly uncomfortable. So in terms of the conditions that were monitored, thanks to the station, at the beginning of the class, at the beginning we were around 28 degrees. In the end of the class, the temperature inside the building was 30 degrees. So that means that in these kind of conditions, at 30 degrees, most of the students felt comfortable. They were asked also in terms of air velocity preference, and 50% of the students answered that they don't need any change, but 43% they would prefer more air velocity. So the next day was another day in February 22, and the answers were less positive than the previous day. You can see the response in the answers in terms of thermal sensation. We had on the class of, let's say, 10 students, 4 of them at the beginning of the class that felt hot. One was very hot. In the end of the class, 3 remains hot and 2 very hot. And the temperature was 30 degrees, but the level of humidity was higher than the previous day. So in terms of thermal sensation, the sensation of comfort or discomfort is mainly affected by the level of relative humidity rather than the level of temperature. And in terms of thermal judgment, we have exactly the same results. We have some of the people felt comfortable and slightly uncomfortable. The majority of people felt comfortable and slightly uncomfortable. Only 2 people at the beginning and 4 in the end felt this environment uncomfortable. Yes. So just to why we had these results? Because we realized that during ceiling fans were not working. We had a problem with the ceiling fans. This is why in this kind of condition, the users were not able to use ceiling fans to balance the effect of the low velocity. It was not a very windy day, and you can see that the answers of the users is really affected by the fact that ceiling fans operates well or not. So this is why you will see in the end of the presentation, I will insist on the role of the ceiling fans, because without them, in case we have no wind, the users cannot control the environment properly. So in terms of lessons learned in this building, thanks to the surveys, I can state that users are overall satisfied with the thermal comfort conditions in summer. We realized that, as in Réunion, we have two very different seasons. We have, let's say, a cold season, and people complain more by the conditions in winter because the wind is really strong and it's really cold. So, and we didn't plan that the users answered it, but we really have to face a problem of discomfort in winter, not in summer. So we have to find solutions to manage the wind in winter. And to conclude this webinar, to summarize all what was explained by Lorenzo, Alessio, and Virginie, this is some common recommendations for. We don't present the 24 case studies, but with the experience of those 4 case studies, we can state that vegetation, planting trees around buildings is very important. As I said, it can reduce the air temperature by 4 degrees. Natural cross ventilation is very interesting option, but we must find a way to manage natural cross ventilation. We realize that, for instance, for the Mbakadu case study, natural ventilation can be used when the temperature outside is below 30 degrees. When the temperature is above 30 degrees, it's better to close windows or to reduce openings and to use ceiling fans. Because when the air outside is too hot, we have to stop it to come in. All those buildings that were presented, they have efficient solar shadings that are used in summer. Ceiling fans must be a solution, a mandatory solution imposed in all bioclimatic buildings in Africa, in Réunion, and in the south of Europe. Ceiling fans is really, really important. I insist on this really. It's not very cost effective in terms of price and in energy consumption. For instance, a ceiling fan consumes 20 times lower energy than air conditioning, 20 times, which is really, really important. So in terms of materials, for climate, tropical and humid, low inertia must be considered. But for hot semi-arid, like in Senegal, a warm temperature climate like in Portugal or in the south, high inertia materials are more recommended. And to conclude all this, in terms of innovation, I did not mention, but the building in Ézirois, we did not invent anything. We just got, and the architect got inspiration from the traditional architecture. The last picture that you can see at the bottom of the slide is a Creole house. And we just have the main feature of the Creole house that were built 1 century ago. The main features were exactly the same that we use now for the Ézirois building. That means that we use vegetation around the building, we use solar shadings, we use natural cross ventilation. So we have to get inspiration from the traditional architecture, and we don't have to forget that our ancestors, as they didn't have the air conditioning, they have to find solutions thanks to the climate. So all those buildings, they have a clear connection with the climate. So we have finished our presentation. I thank you, Lorenzo, Alessio, Virginie, for those presentation. And we have 15 minutes to have a discussion with the people that attend this webinar.
Yes, thanks to all. And yes, if there are questions, please, you can intervene. There is, in fact, one question in the chat from Dr. Umaira Mughal on the possibility. I don't know if Virginie and François can see that, on a suggestion for considering also wind catchers in a case when there is this directional wind coming. I don't have a quick answer for that, but I guess this is a case where other ways to catch the wind can be considered and evaluated.
Alors, so I just reread the question of Dr. Umaira Mughal. Plants may reduce the temperature of wind by adding humidity that is coming from the window and moving towards the top of the chimney. We don't, plants, let's say, due to our experience, we don't have any reductions in terms of wind. So the trees don't block the wind, but we have to select, let's say, that they may have the risk, but so we have to work with people that are familiar with which trees we have to plant around the building. But in La Réunion, we don't have any negative effect due to the trees. So the question is, maybe a wind catcher is a better option in this case. We don't use wind catcher. So the natural cross ventilation is really efficient. For me, the wind catcher or maybe the low pressure shaft. So maybe by wind catcher you mean, is there a difference between a wind catcher and the low pressure shaft that I presented previously? I don't know if there is a difference. In any case, for me, the natural cross ventilation is really, let's say, the most efficient option. And we don't have any problems with trees that block natural cross ventilation. And the main effect of the trees is to create a shadow effect on the surrounding of the building to avoid to have these hot surfaces that create this hot air and enter in the building. Even if we have a dense vegetation, we don't really suffer we don't see a negative effect about this this vegetation. I'm not sure if I answer correctly to the question, but as I said, due to our experience, we don't have a negative effect of the vegetation.
Thanks, François, and I think it will be interesting to go on with the analysis of the data, also the correlations we have been able to find till now are probably only preliminary results. So there will be a final report on the monitoring and more discussion. So we could try to obviously to take profit of the comments we are receiving. Dr. Umaira will also join our team in the near future, so we can have and also others might comment on the records that are on the website. So comments and suggestions are definitely welcome towards the end of the project, where we will try to incorporate as much information as we can. Are there other questions on from the audience or comments? Feel free to send your comments on the chat or to raise your hand, and Camilla can allow you to. Okay, we have a question. I don't know if you want to write down something or intervene directly, and I don't have the control on the microphones.
Yes, I just allowed Mansour. If you want, you can activate your microphone and speak. Speak up your question.
Yes. Good morning, and thank you very much for your presentation, which is very interesting. I have asked 2 questions, and I have a third one. For the Senegal case, I don't see a very significant impact of the high inertial material, because I have not realized a phase shift on the temperature between the 2 curves you have shown. We have a very good impact of the attenuation, but the shape shift is not there. Maybe I have not seen it very well. The second question is when you use the tester device, to measure internal comfort, you should have what they call the PPD and PMV curves. Do you use them to correlate with the interview you are doing with the people, the occupant in the case of La Réunion, for example?
Okay. Thanks for your question. So the first question concerning inertia for Mbakadu, yes, we, as Virginie has explained, of course, there's no, in the case of we have high thermal inertia, normally we see a shift between the maximum of the outdoor temperature and the maximum of indoor air temperature. You're right.
Yeah.
We don't see this shift, but the second effect of thermal inertia is that the difference between the maximum of the indoor and the maximum indoor temperature and the minimum is much more lower than the difference, the amplitude outside. I agree with you. There's not a shift. I have no explanation about it. But in terms of difference of temperature, we can see the effect of inertia, because the high inertia materials, they act as a kind of filter for the outside temperature. So we see one effect, but the second effect of the shift temperature we don't see. So
if I can try to support François, probably we try to discuss that in another occasion. In Bakadu, given the ways the building could be realized, given the boundary conditions of that site, the windows are completely open all the time. So also during the day. So obviously part of you have the outdoor air, even if the windows are not too big, but there is a direct connection between indoor and outdoor during the day, which obviously cancels out this possible time shift. That might be one explanation. As I said, we are just at the preliminary analysis. It took a lot of time to install instruments by the various teams. So we have just received the data. Some of the data are very fresh, and we have to. That's one.
Just to tell you that I am facing the same problem, because I have tens of measurement on some buildings in Senegal, and I have the same problem. And the final conclusion that I had is what you just say, Mr. Lorenzo. It is the influence of the air conditioning. What do you say? The local was open and we have an influence of external air, external ventilation coming inside inside the building. But I'm pursuing the research to find out exactly what is the problem. So for the second question, the PPD and PMV curves, do you use them?
No.
No. Okay.
We deliberately are not adapted for hot climates. Fanger has developed PMV and PPD for European conditions and cold climates, but for warm conditions, the PMV and PPD are really not adapted. So we use the Givoni comfort zones as a tool, but really don't use them because they have a tendency to overestimate the real answer of the users. Because they have been developed in steady state conditions. And when we use air velocity, we have very transient conditions. So the thermal sensation of the user is really affected by the air movements inside, and we are not in steady state conditions. We are always in transient conditions, in tropical conditions.
Yeah, I am on this. I am also on this research also. I'm using them, and I'm trying to see what is the problem. Okay. No, thank you very much.
I suggest not to use those index. Really, they are the research references have shown that they are not adapted to hot conditions.
Okay, thank you very much.
You're welcome.
Okay, I don't know if there are other questions on this issue of comfort. Obviously, you can also have a look, Mr. Mansour, on to the reports from ABC 21, where there is one on comfort indicators, and you will see that recent standards propose the adaptive comfort model. There is the Givoni tables shown by Professor François Garde in Virginie. And Fanger himself was proposing an adaptation of his index in warm conditions. There is a paper from Fanger trying an adaptation. Again, we don't have probably time, and there is another question, but I suggest you to consult this summary on comfort indexes that you can find on the publication page of the website, and we can discuss it more in the future with pleasure. There is another question, I guess. Can't see exactly.
Marina, you should be able to activate your microphone.
Yes, thank you. Thank you so much for this very interesting presentation. I wanted to ask, you mainly spoke about ventilation beside the building envelope as an energy conservation method. So my question is, if it is not mechanically controlled, won't it be strongly dependent on the user behavior, especially also cross ventilation and so on? And also, if at some points airspeed would be too high or the wind would be too strong, that we might need magnetic doors. One that also affect the comfort inside the space, especially in an office with papers, tools, and so on.
Yes, so I often say we are not. I'm not. Let's say favorable of controlling every. I often say that we have been used to be passive users in active building. We have to change our way of living and working in building. We have to become active users in passive buildings. And this is really important. That means that louvers we don't need to have mechanic control louvers, for instance, because we have still a brain, and so we have to, if it's too windy, we just stand up and we close. In the room, you don't see because we have the ABC21 background, but we have louvers, we have ceiling fans, and if it's too hot, we open louvers to create velocity. We put the ceiling fans on, and we do this by ourselves. We don't wait that we have a message on the computer screen that asks it's too hot, open the windows. Our ancestors, as we said, we try to reconnect with the climate, and because of air conditioning, we lost this connection to the climate. So we have to have this active behavior in the passive building. This is my answer.
But don't you think that that needs a certain level of awareness from the part of the users? So not everyone is aware of the importance of ventilation.
Yeah, I agree, because even for instance, some of my students, because in the Ezira building, so all the classrooms are naturally cross-ventilated, and sometimes in terms of behavior, I can see classrooms where all the louvers are closed and the ceiling fans are on, because people, they have this let's say behavior of when I enter in a room, I'm looking for air conditioning. We've been educated like this, and so I tried, and we, as I say, we lose that what was natural. My parents, or maybe your parents, it was very obvious that I'm hot. I open first to create air velocity, and then I use ceiling fans. So we try to educate the students. Some years ago, we printed some sheets that were inside each classroom, and it was mentioned: you are hot. 1, open the louvers to create air velocity. 2, use ceiling fans. And so we had to write this, but it's let's say we had for me, we don't have to use that, but because, as I said, we lose this kind of normal behavior, we have to re-educate the users and the students to this. So the solution is education, and to communicate, like I said, consumer direction.
Yes, I understood your point. Thank you so much.
You're welcome.
Okay, and there are other comments. I don't know how much time we still have. Interesting comments on reducing the air temperature of incoming air with some evaporative process, which was already presented as a suggestion by François before, but here there are Mr. or Miss Reisdal who is proposing the use of simple evaporative cooling techniques, which are also to be considered for sure. Again, I don't know if François and Virginie have comments on this. I can only see they are certainly part of the things to be explored in climates where air is dry, as we are seeing in some parts, obviously.
Yeah. I am reading what Mr. Reggiali has written, and thanks a lot. because it's very clear what you said. But I completely agree with you. We have to take inspiration from the traditional techniques, like, as you say, moucharabier, the wind catchers. I completely agree with you. It works when the outside temperature is above 30 degrees. So we have to use those techniques in the modern buildings. This is exactly what we did in the Zero building, but we are in a tropical and humid climate. For hot and arid climate, yes, of course, I agree with you. We have to use these passive solutions, moucharabier, dome shaped ceilings, and they use also direct evaporative cooling with water. So the question, what do you think about such ventilation techniques in really high temperature? But I think the experience and show that they are very efficient. So we just have to use those techniques. I'm not an expert of hot and arid climate. I'm more an expert of tropical and humid climate, but those techniques have shown they are really efficient. So I saw some papers which dealt from these old and ancient techniques have been monitored, and they prove they are efficient. The only difference between what happened centuries ago and now is that now, let's say the policymakers, we need to prove they are very efficient. So we need to measure and to quantify the efficiency of those techniques. 20 centuries ago, people knew it worked, but now we have to prove they are efficient by saying we can reduce the temperature by 4 or 5 degrees. But we know that work, but we need to prove how much temperature we gain thanks to techniques. But yes, my opinion is that we have to get in, of course. Not sure if that answer to your question.
Okay, yes, there are other questions. And let's say a general question probably for closing is that the ancient wisdom is telling us that for each climate and each condition over the year, because obviously in these warm climates we might have a hot, dry period and a humid period, and in those two different periods of the year the strategy might be different. So the answer is a composed answer which replies to each climate condition with a specific recipe and a specific management strategy for that situation. We think we just offered today some examples within a selection of conditions, and the entire spectrum is in the hands of the people who are intervening, who are certainly already working in designing and operating buildings in warm climates. And we will try to summarize as far as possible in the guidelines other possibilities, other examples, other climate conditions. There are also already a number of published books and papers. At the beginning of the guidelines, there will be a selection of existing literature, and for example, Alessio is working on part of it. So we're trying to not only to offer what will come out of our small measuring campaign, but also what has been obviously produced before. Yet, some of these new buildings, like the ones that, for example, François has shown for a tropical climate with, which is not dry, where the wind, so the leading force is the wind, then there is an appropriate solution that in La Réunion they are developing, testing, and testing also with interviews to the occupants. So we hope that for some of the climates we might offer some new information, and obviously we will try to we are trying to offer a review of other analysis made before, and you will find this in both the report on the case studies, the report on monitoring, and the report on review of existing guidelines with some updates to radiation to the sky, to ventilation in tall buildings. So we hope to offer some new information, and the evaluation will be from the readers, from the people who have participated today, and we hope the conference will be definitely another opportunity to share our experiences with the other designers and researchers. So there will be more from the team of La Réunion, there will be more from the other teams in Senegal, Morocco, Italy, and Portugal. And we hope there will be more from all of you. Again, it's possible to share your experience and your reflections and your questions via the abstracts that can be sent to the conference within 14th of April. And that's probably the most important thing, that we can continue this exchange and trying to ameliorate our capacity to adapt to the buildings, to the climate. I don't know if we have more time. You can find in the chat where to download the reports already produced, and also in the same website. For example, there is a page on case studies where you can find the work that has been coordinated by Virginie and François on case studies, and where many have contributed. And you can find a page on the conference, to which, again, I invite all of you to participate, possibly in presence in Morocco, but there will be also part of the sessions will be available in hybrid format. So there will be also a possibility to follow part of the presentations in remote. So I don't know if Virginie and François or Alessio want to add other things.
No, I just want to thank all the participants, and maybe to complete what you said, Lorenzo, I think one of the main outputs of this project, ABC21, I mentioned as an introduction, is that thanks to this project, we get lots of monitor data in African buildings. And as I said, before this project, it was really difficult to find in the bibliography measure data. So this is one of the main outputs of this project, and in the end, we will be able to share those data, those post-occupancy evaluation feedbacks with all the people that will be interested in improving the bioclimatic behavior of buildings in Africa.
And absolutely, and in Europe also, because obviously in certain parts of Europe we can use that, and we probably need to learn because some of the mainstream architecture sometimes is not providing the expected comfort and energy performance. So it's a process which involves both the bioclimatic architecture and the other types of architecture that can benefit from partially maybe applying the passive techniques that we are discussing. So for me, this would be probably given the time we have enough. I see still a lot of people online. Thanks a lot to those who have followed. Feel free to send us other comments if you feel via the website and the contacts there. And we keep this webinar, we did more or less within the time frame we had decided, but there were useful and interesting comments, so it was good to extend a bit. Again, the next opportunity will be, I guess there's still one webinar, we will announce that, but definitely the conference will be the next possibility of exchange, and we really hope to have lots of people to bring in their knowledge and take profit of what we have been able to produce within this, in fact, small project, but try to produce as much as possible with the resources that were available. And so there's been a lot of effort from many partners. There are some online from Senegal, Ernest, others present here. So for me, I would conclude, if there are no other comments from other partners or participants, then we can thank everyone and possibly au revoir at the conference. See you at the conference.
See you.
Thank you all.
Bye-bye.
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 Bye.